Very much, Sammy, and thanks for delivering about 3/4 of my talk in the title already. Yeah, so I'm going to talk to you about what Sammy just said today, and just before we start, I'll just give it a little overview of what I mean by this. So by calibrated, I just mean representations that have some idea of an uncertainty quantification. And by active learning, what I mean is it's machine learning, but it's machine learning that chooses the next data point in a kind of sensible way or in some kind of principled way, so that we can use smaller data sets for training our models. But anyway, hopefully that will become clear as I go through the talk. So yeah, just before we jump into all of that, I think one of the important things I'd like to draw out is the difference between, or what deep learning is in terms of machine learning. So you might hear the terms used and think they're kind of interchangeable. And I'd say that actually what deep learning is kind of like a subset of machine learning, which is again a subset of artificial intelligence and so on. And the best way, one of the major distinctions between deep learning and kind of other types of machine learning, I would say, is to do with how you come up with features that are used in the model. So I've kind of represented this problem here on the right with a classic kind of classification type of problem. So we've got a picture and we want to classify what kind of animal is in the picture. So in kind of classical machine learning approaches, what would happen would be that you would featureize the, so hopefully you can see my laser pointer. So you would featureize the picture yourself. So you do something like you take a look at it and you tabulate the number of eyes, whether it has whiskers, number of legs, fur, scales, and so on. So you hand featureize your picture. And then based on that kind of tabular data, you feed that into some kind of classification model, which could be something like a decision tree, which asks the questions and then comes up with some kind of classification, and you get a class out at the end. Now, deep learning, on the other hand, doesn't rely on this kind of hand featureization. What you feed deep learning is actually just the picture itself. So you just feed it this picture, and then it learns from the picture to put it into a different kind of class. And so the beauty of deep learning is that it obviously requires a lot less manual input in terms of featureizing, but the difficulty is that generally comes at the cost of requiring a lot more data to train the models. And I should say that this process whereby deep learning doesn't require kind of hand featureization, it's quite often referred to as feature learning or representation learning. Okay, so that kind of deep learning has started to become more and more prevalent in material science, and it's no surprise that's kind of happened as data sets have become available and have grown. So the original success of deep learning, so deep learning approaches like deep neural networks have existed since at least the early 1980s, but really when they started to become popular and to really realize their potential was about 7 or 8 years ago, when we started to have very large curated labeled data sets, like ImageNet is a famous one for image-based models. But now it's becoming more and more popular in areas like material science, where we have more and more labeled data sets, large data sets that can be used to train these types of deep learning models. And the particular type of deep learning that we're interested in and that we're using here is called a graph neural network. So graph neural networks essentially can represent some system as a graph, so with just connected nodes, and then those nodes do what's called message passing between each other. So when you're training the neural network, what it's doing is learning how the different nodes connect to each other and pass information from one to the other. So you can see that kind of maps very naturally onto chemical or material structures. So you can represent them as graphs and talk about how the different atoms in the graph talk to each other. So graph networks, actually, because they build in and they codify something of the kind of physics of the system, actually already need a little bit less data to train them than traditional deep neural networks, just because you've imposed some kind of knowledge in there already. So yeah, deep networks are great and really, really powerful and had lots of success, but they do also have some serious and worrying shortcomings, and one of them really is to do with the lack of any concept of uncertainty quantification in the results that you get from deep neural networks. So I've given this example here, and this is a real example of a deep neural network that's trained to classify pictures of animals, and it's given this picture of a panda, and it classifies it in the first case, and it says it's 57.7% confident that this is a panda, and that's correct, that's great. But then if we just sprinkle a little bit of noise, so this is just white noise, and we sprinkle a little bit of that on the picture, now to your eye or my eye, these pictures haven't changed, and that still looks like a panda. But suddenly the deep neural network is predicting that this is a gibbon with 99.3% confidence, and that's pretty worrying. That it's not only getting it wrong, it has high confidence that it's getting it wrong. And this kind of thing is known as adversarial noise. So it's noise that comes in and can throw the model right off its predictions. And other cases, other things that can happen is that you get an example of new data that's outside of the distribution of the kinds of data that you've trained the model on. And the model has absolutely no way of telling you that this is outside of the distribution, and it just gives you some answer, which looks like a very confident answer, but it may well not be a confident answer. And the problem here is that the neural networks are kind of inherently overconfident, and particularly in things like these classification tasks. So I show here a kind of schematic of a neural network at the top, and in this section here, it's doing that representation learning that I was talking about, and then it's fed into some part of the network which does the function approximation. And the function in this case is that you want to classify it as either red or green, and this kind of neural network structure is doing that approximation. And the reason it becomes overconfident is that classification tends to be based on a function like this, which is the sigmoid function. So you can see it plotted here on the right. And the whole purpose of that sigmoid function is to take any value that comes in and kind of, force it to be close to 0 or to 1. So to force things to separate out separate classes and to force them as far away from each other as possible. And so it tends to make the prediction made by the neural network look more confident than it actually should be. So one of the ways, or one of the methods that you can use that kind of overcome this lack of uncertainty quantification, so UQ here is on uncertainty quantification, is a process called, or a method called Gaussian processes. So Gaussian processes are a very nice set of methods which are based on Bayesian statistics. And what's really nice about them is that they give you a prediction, but they also give you a confidence interval on your prediction. So here is at the top is a simple example of the blue line in the middle is the true function. The red X's are the points at which you have data. And then the kind of the shaded background is the estimate from the Gaussian process. And what you can see is at the points where you have data, the Gaussian process is very certain, and it's very certain of the right prediction of the function. And then as you get further and further away from points where you've actually measured anything, you see your uncertainty rises with that as well, which is very nice. And that's something we would ideally like to be able to have with our neural networks. Now the problem, or one of the drawbacks of Gaussian processes is that they're very much like these in the family of these classical machine learning approaches. They generally require small handcrafted feature sets to go into them, so not ideal in terms of dealing with large amounts of data. So what we'd like to see is, can we get the best of both worlds? So can we combine deep learning with a Gaussian process and then get something which automatically learns a representation, but then feeds it into a model which gives an uncertainty quantification? And that's exactly what the method that we developed here is doing. So we take our input structure, which is just a material structure, some kind of CIF file, and it gets passed through a graph neural network, which in this case is based on the MagNet GNN structure, which is a previously developed graph neural network from a group in the US. And what we do is it kind of, MagNet takes it and learns representations, and then usually what MagNet would do would be to feed those representations into a standard feed forward neural network, or what's known as a multi-layer perceptron, and then make the estimation, and it just gives a single value. But what we do instead is kind of intercept it and take this representation that it has learned and use that vector that it has learned as the input to a Gaussian process. And then we use that Gaussian process to do our property estimation. And it gives us not just the property, but also an uncertainty on the estimation that it makes. So how does this work? Is this a reasonable thing to do? So the first thing we can do is actually take a look at those vectors. So I'm basically taking this vector here that I've intercepted, and I'm projecting that into a lower dimensional space. And I want to see, well, does that have some relationship to the property that I'm interested in? So I'm interested in formation energy. And you can see that that vector does have some kind of spatial relationship to the formation energy. So I can have some idea that, okay, doing this is a relatively reasonable thing to do. Of course, the real test is to then use this to make some actual proper predictions. So we can make some predictions on a test set which was not used during the training, and here we have on the left we have the predicted energies, formation energies from our GNN plus Gaussian process, and these are the DFT energies are the training energies, and you can see it's doing a rather good job of making those predictions. So a pretty small mean absolute error. It's actually comparable to state-of-the-art graph neural networks which don't provide uncertainty quantification. And then finally, of course, importantly, the uncertainty quantification that it provides. So we can look at that. So this plot at the top, I've taken, I think it's about 100 of the predictions from the test set, and we put the error bars onto them. So those error bars are just twice sigma, or twice the standard deviation. So based on simple Gaussian statistics, 95% of your predictions should fall within twice sigma if the process is indeed Gaussian. And it looks very much like that. If there's 100 points here, I can see a couple of points here where maybe the points, the line doesn't fall within the error bars, but for most of them, the line falls within the error bars. And actually what we can plot at the bottom here is the, so delta EF here is the error. So that's the difference between the predicted and the true error. And along the x-axis here, you have the predicted uncertainty. So you can see the ones that have the largest error are also in the region with the largest uncertainty. And there's a couple of cases where it's done particularly poorly that I've highlighted there. I won't go into too much, but they seem to all have this kind of phosphate motif involved, which may be just that was a very underrepresented in the training data set. So the model doesn't do a very good job of predicting the energies of those phosphate type structures. And so the actually what that leads on to is the concept of active learning. So, oh, and this has turned to a nice purple, very nice. Active learning is the process of, when I'm training my model, I would like to choose new training data which will give me the largest amount of new information for the model. So if we think back to the kind of picture of the Gaussian process from earlier, which is quite small on this slide, I understand, but if you look at the function there, ideally the next point you'd choose, you'd probably want it to be somewhere out here on the right hand side of this this plot, so that you can maximize the amount of new information that you get, or maximize the amount of uncertainty that you remove. And that's what we mean by entropy based. So here entropy means uncertainty, and we base our next choice on the kind of instance with the largest uncertainty. And in terms of our material space, that may well be one of these materials. So if we look back at this slide here, these materials have pretty large uncertainties associated with them as well. So we would maybe be able to choose them in some way based on the uncertainty, and then use them to retrain the model. And then the model is suddenly able to make predictions on that kind of phosphate type motif. And this is the active learning procedure. So you have your machine learning model, which makes predictions based on some kind of input. Those predictions provide you with an uncertainty quantification. Based on the uncertainty quantification, you choose the next experiments to do, you obtain new labels, you retrain your machine learning model, you make predictions, and you go around and around like that. And actually, this is the kind of workflow that we have set up. So we have some database here of labeled data, so that's DFT formation energies. We feed them to our neural network, so it does the representation learning, pass that to the Gaussian process, which gives us a prediction of the property and the uncertainty. And then we have a large database here of unlabeled materials, which don't have the properties associated with them. We pass all of them through the neural network. We get predictions of the property and the uncertainty. And then we choose the ones with the greatest uncertainties, and we actually go and do a DFT calculation for them. They become part of the labeled data set. We retrain the model, and we go around in a loop until some prescribed time in the future when we're happy with how our model is performing. And this is actually just a demonstration of how the entropy-based active learning performs. So here we have increased our training set, and we've done it using two procedures. So in the orange plot, we have just randomly chosen the next material to add to our training set. And in the green plot, we have used the entropy-based active learning to choose the new material to include in the training set. And you can see that it works, the model improves significantly quicker if we do this entropy-based active learning approach. So a 43% improvement over 1,500 cycles. And actually it achieves the same performance as the random selection with fewer than half the number of additional training samples. So quickly, just on to the conclusion. So deep learning is great when we have lots of data. Gaussian processes are great when you have a good representation. Deep learning plus Gaussian processes can give you the best of both worlds. And by having some kind of principled uncertainty quantification, we can do smart sampling procedures, which allows us to use much smaller data sets for training equally effective models, which is great in a scenario where obtaining labels for data is expensive. And I'll finally finish up by giving the acknowledgements. So the vast majority of the work here was done by Johannes Alate, who's a CDT student at Bristol and was working with us for 6 months. Alex Moriarty at Imperial College was a summer student actually, and he wrote a modular version of the GNN plus Gaussian process, which I'll give a link to in the next slide. The whole of the scientific machine learning team who I work with, and also the Alan Turing Institute for funding as well. And the if you want to know more, there's a preprint of the paper just out a couple of days ago. There's a Git repo associated with the paper, which you can find there. And also there's this Unlock GNN, which is Alex's kind of modular version of the Gaussian process plus GNN, which should make it somewhat easier to work with. And thank you all for your attention.